finish. How long do I have? Not
40,
including questions.
about 40 minutes.
Okay.
Okay, I'll send you a reminder when 5 minutes are left.
Sorry?
I will send you a reminder when 5 minutes are left.
Okay. But then should
Okay.
I spare a few minutes for questions or can I talk for
Yeah,
45?
yes, if you want, you can talk for 45 minutes. So we are informal regarding the time. Don't worry. Yeah.
Okay. Okay, great.
Okay, good. So let's begin. Welcome everybody to this week's Majorana-Raychaudhuri seminar series. We are very happy to have our first speaker for today, Paula, and she will be talking about constraining the bispectrum from bouncing cosmologies with Planck data.
Thank you for the nice introduction, and also thank you to all the organizers for the invitation. Also, please feel free to interrupt me in case you have questions during the talk. So today I would like to present a couple of publications that were done in collaboration with Ruth Duhe, Nelson Pinto Neto, and Bartjan van Dent. And our main goal during these projects was to find some imprint from bouncing cosmologies and especially quantum bouncing cosmologies in the CMB and try to somehow connect such high energy scales to phenomenological physics and cosmology in such a way that we can have some probe, some way to test and possibly constrain these scenarios. And in these projects, what we found is that indeed this can be done. And I'm going to explain why, although in such a high energies, you can still find imprints that are still visible and constrainable with current data that we already have, for instance, as Planck. So first of all, I'd like to start with CMB basics, and then I'll move on to the CMB anomalies on large scales, because these are features that motivated these bouncing scenarios that were proposed that are based on loop quantum cosmology, but they are also very interesting from the phenomenological point of view, because they alleviate such anomalies that are present in the data. And then I'm going to talk a little bit about these scenarios. And then we are going to see how the reduced bispectrum looks like in these scenarios, because this is the quantity that we actually measure, and then compare it with the Planck data. And finally, I'll discuss some implications for loop quantum cosmology, which is the main theory behind these scenarios, and some recent updates that appear in the literature. So starting with CMB basics, we know that in the very early universe, we had this very hot plasma of protons and electrons, and then photons keep scattering all the time. They don't have a long mean-free path in such a way that they cannot reach us nowadays. And the universe is kind of opaque to photons. But when the temperature decreases, we have recombination, which is this combination between protons and electrons. And then these photons finally can travel and they reach us nowadays. And they form this last scattering surface, which we radiate as a black body. Nowadays, it's in the microwave frequency range. And because it comes from every direction, we call it the cosmic microwave background. And here in this figure from COBE, we have the monopole, which is the mean temperature that we have from the CMB. Then if you go to anisotropies that are a bit smaller, you find a dipole, which is because of our motion with respect to this background. And then if you go even lower, you start to see these cold and hot spots in the CMB, which nowadays with Planck, they are very precise. They go up to 10 to minus 6 Kelvin. And we have this map of the sky, of the anisotropies of the background that we can use in order to probe the primordial perturbations. So if we start getting 2 points in the sky and correlating them, we will have the 2-point correlation functions, which can then be translated to the power spectrum. And here we have this figure that is very well known, which is the CMB power spectrum. And here we have the Sachs-Wolf plateau. And this part here represents the very large scales that were outside the horizon during recombination. And then we see the acoustic oscillations of the modes that were inside the horizon. And then these peaks are used, for instance, to constrain cosmological parameters. And the plateau here, as we can see, has very large error bars. And this is mainly because of cosmic variance, which is this intrinsic difficulty that we have to measure points in the sky that are very separated, so very large scales. Because we only have one sky to look at, so we cannot have an ensemble of universes where we can make the measurements on. And then you have this intrinsic uncertainty in the measurements that is represented here by these large error bars in this Sachs-Wolf plateau. And this is the main difficulty when we want to constrain physics that only appears on very large scales, because you can have some new physics here that changes a bit the form of the plateau, but if cosmic variance dominates, which is usually the case, you cannot constrain this new physics that appears only in this part of the power spectrum. On the other hand, we can also correlate more than 2 points. So for instance, if we start correlating 3 points in the sky, we'll have the 3-point correlation function, which is then related to the bispectrum. And then we usually classify this bispectra in terms of the triangle shape. So you get these 3 points in the sky, you see the shape of the triangle that it forms. And then we have, for instance, the squeezed shape, which is this one with one small side and the other two comparable, or the equilateral shape where all of the 3 sides of the triangle are comparable. And then there is one type of non-Gaussianity that is, I would say, the most popular in the literature. It's the local non-Gaussianity, which is formed if we get a Gaussian field. So this psi g, G stands for Gaussian. And then we construct a nonlinear combination here, and we quantify this term here by means of the parameter f and L. Which then tells us how strong this non-Gaussianity is. And this we just, the second part here, the second part here we just add in such a way that if you get the mean, you still have a zero mean for this non-Gaussian field. And this is a number usually, but it might have some scaling dependence in some scenarios, which is exactly the case of these bouncing scenarios that we are going to see. So now let's move on to the CMB anomalies on large scales, which are features that they appear in the data. And the main point is that they have a very small probability of happening in lambda CDM. So if you assume that lambda CDM is the cosmological model, then you have a probability that is usually quantified by means of p-values that are lower than 1% for lambda CDM. So in this sense, they are considered anomalous. Their significance is not huge, but they are still not common features if you consider a concrete realization of the CMB map, assuming lambda CDM. And the first of these anomalies is the power suppression, which is this absence of the 2-point correlation functions in angular scales that are larger than 60 degrees. So if we see this plot here from this paper, we see that we have, here it's just information regarding different maps, but these are the observational data that we have. And in blue, in this dotted black line, we have the lambda CDM prediction. And here we see that lambda CDM would expect something much larger than what we actually observe. So we usually quantify this lack of 2-point correlation functions by this estimator, which is the S-half, where we just integrating these angular frequencies larger than 60 degrees. And then what we see in the data is this value here. And what is expected by lambda CDM is this value. So we see there is a discrepancy. The second anomaly is parity asymmetry, which is an odd parity preference in the data. And what this indicates is that there's some kind of isotropy violation at these scales. So what we do in order to consider this anomaly is to get to the temperature field, and then you check the parity properties of the temperature. And when you go to spherical harmonics, you can see this by means of the multiple L being odd or even. So we quantify the parity of the temperature field by means of the odd or even multiple. So we have this estimator here, the RTT, where he's just for temperature, and then these D plus and D minus, they are related to the power spectrum here up to some maximum multiple that will sum only on even multiples for the case of the plus and only on odd multiples for the case of the minus. And then in lambda CDM, the expected value is 1 because in principle there should be no parity dependence on lambda CDM, so you have parity neutrality. But when you have the D plus, it means you have an even parity preference, and when you have more D minus in such a way that the estimator is smaller than 1, you have odd parity preference. So this indicates some parity that exists in the data that should not be there in principle for lambda CDM. And then the final anomaly is the dipolar anomaly, which indicates a correlation between multiples L and multiples L plus 1. And this one indicates there is a violation of isotropy. This is called dipolar anomaly, but it's not really related to the dipole in the sense of our motion with respect to the background, because this is quantified in a different basis. So instead of using the usual spherical harmonics decomposition, we consider the bipolar spherical harmonics, which are these quantities here. And then they have this capital L and M in order to write the decomposition in this basis. And then we have these coefficients, which are the Clebsch-Gordon coefficients. And then when you have a correlation between L and L plus 1, what you get is that this capital L here will be 1. That's why it's called the dipolar anomaly. And then if you correlate then the two-point correlation function for the temperature anisotropies by means of these harmonics, you get these coefficients here, which are the bipolar spherical harmonics coefficients. And then they work very similar to what people usually do, for instance, for the spherical, the usual spherical harmonic decomposition. But here the main point is that for lambda CDM, you only have this coefficient. This is the only non-vanishing one. And you can get this by means of the properties of the Clebsch-Gordon coefficients. But what we see in the data is that if you get the coefficient where the capital L is 1, so this one here, you get, so you will define this estimator, but it's essentially measuring this coefficient, then you get that this one is non-zero, which is not expected in lambda CDM. And here we have these results from the Planck 2015 paper. So these anomalies, they are unlikely to happen in lambda CDM. Some people might consider that they are some statistical fluke because they are still possible in lambda CDM. So you can just consider that in some concrete realization it happened, that these anomalies are there. Some people might say that the significance is not so strong, but the fact is that they keep appearing in different surveys, so COBE, Planck, WMAP, and you can ask yourself whether they are caused because of the presence of new physics on such large scales. So one of the proposals in this direction is a bouncing scenario that will replace the Big Bang singularity. So you start with a contracting phase, you reach some minimum value for the scale factor, and then you have the usual expansion history. And this singularity is replaced by some new physics. It could be because of quantum gravity scenarios or modified gravity scenarios. And one example is the one that comes from loop quantum cosmology. Sorry. the one that comes from loop quantum cosmology, and this is the main one that motivated the scenarios that were proposed in this context in order to mitigate the CMB anomalies. So here we have the scale factor for this bouncing scenario that was proposed by Agulu, Kranas, and Srinath, and here we have the parameters B and N, so they will give you the information about the bounce. So the parameter N is related to the kind of bouncing scenario that you have. So for loop quantum cosmology, N is 1/6, and B will be related to the curvature at the bounce. And this is the scale factor at the bounce AB. So here, just for illustrative purpose, we have the N 1/6, which is the loop quantum cosmology bounce, and 0.21, which is a phenomenological bounce that we are going to see in a minute. And here we see that the singularity is replaced by a minimum scale factor. So the main point of this scenario is that you set the initial conditions in the far past, and this will be the usual Bunch-Davies vacuum, but then once it evolves and it reaches an inflationary phase that happens after the bounce, this vacuum has already evolved. It's not an adiabatic vacuum anymore, and then it introduces non-Gaussianities in this scenario. And these non-Gaussianities, they will correlate modes that are outside the horizon to modes that are inside the horizon and are present only on very large scales. And because of that, because of this correlation that you have from super-horizon physics and very large-scale physics, you can modulate the power spectrum on such very large scales where the anomalies appear. So the main point is that the FNL that they get, which quantifies the non-Gaussianity, is scale dependent. And as we are going to see in a minute, it behaves in such a way that it's very large on very large scales, and then it decays very quickly inside the horizon. So the main point is that you have very large non-Gaussianities outside the horizon and on very large scales, which are expected to be covered by cosmic variance in such a way that you don't see them. And then when they decay and they are inside the horizon, they are still compatible in principle with the data, both on the power spectrum and at the bispectrum level. So this is usually done by considering a spectator mode, which is this phi q here. And this mode, what I mean by spectator is that it's present in a concrete realization. So we don't consider this field as a statistical field. You consider a concrete realization of this mode Q, and then this mode will be correlated to some other modes that are inside the horizon because of the presence of the non-Gaussianity. So if you compute the two-point correlation function for these two phis here, so K1 and K2, assuming the spectator field Q, you get the usual contribution to the power spectrum plus an FNL contribution that is related to this spectator field and the value of FNL. And then you create this modulation that if you go now to the temperature decomposition in spherical harmonics, you get the ALM coefficients, and then you get this modulation here in the CMB power spectrum. And this will be related to the coefficient we've seen previously and also the Klebsch-Gordon coefficients. And then what happens is that you have a CL, which is the power spectrum, the CMB power spectrum, which is modulated. It is formed by the usual CL, so the one contribution here, plus some modulation that we are calling delta L. And then we assume that this delta L is represented by a Gaussian with a zero mean and a variance that can be computed, and it's proportional to the FNL, so the strength of the non-Gaussianity that you have. So this means that on average, this scenario is still isotropic. It still has the null parity, so it's expected that you don't have any parity issue. But what happens is that in a concrete realization, because you have a variance that will be large depending on the value of the FNL, then you introduce a larger chance that in one concrete realization, you get such anomalies in the bouncing scenario. So if I have a very large value of FNL, I will have a very large variance, and then in one concrete realization, I modulate the CL in such a way that I get the anomalies. So what Agulu and collaborators have done in this sense was to consider different bouncing cosmologies. So here we have two examples. The first one, loop quantum cosmology. The second one, the phenomenological bounce. Gamma and Q are parameters related to N. So they assume these values depending on the scenario that you have. And here we have the values of FNL but related to some curvature at the bounce that is obtained by requiring that you have a 20% probability of getting the power suppression. So now, instead of having the p-value of 1%, which is the one that we have in lambda CDM, we require that I want, for instance, 20% probability of getting these features in a concrete realization, and then I will obtain a value of FNL that corresponds to this 20%. And then this is the value for loop quantum cosmology with this curvature. And then if you change the curvature, you also change the value of FNL required. And for the phenomenological bounce, we have these values here. This phenomenological bounce is a phenomenological scenario, so it's not theoretically motivated. It's obtained by the best fit to the power spectrum data. And it is phenomenologically interesting because it fits the data even better than lambda CDM, especially on those large scales where it alleviates the anomalies. So these are the two scenarios that we are going to consider, and then in the end I will comment on other possibilities that one could have for this value of n, which is related then to different bouncing cosmologies. So the power spectrum that we have in this scenario has these three different regions, because once you insert the bounce, you have another scale in the problem. So this part here is related to the bounce scale, which is chosen to be the pivot scale in such a way that you have these modifications mainly on outside the horizon and on large scales. And the other scale here is the one related to the inflationary phase, which is a very small scale. And this part here is the usual almost scale invariant part, which is responsible for the physics that is already in agreement with the data. So the scales that are not so large and they are in principle not related to the anomalies. And then if we get this power spectrum here and compute the bispectrum, you have this expression where here we replaced the scale-dependent FNL by this value of FNL, which is just a number, and this part here, which was the scale-dependent part. So here we have a sum of K1, K2, and K3 divided by the scale of the bounce KB, and this parameter gamma is related here to the kind of bounce that you have. And then this is the primordial bispectrum. And then what Agulu and collaborators found, yeah?
Okay.
Is it a question? Okay, so I'll continue. So what Agulu and collaborators found is that by doing that, by requiring that you have a bounce preceding inflation, and requiring that you have a 20% p-value for the power suppression anomaly, you not only alleviate the power suppression anomaly, but also the two other anomalies that I mentioned, and also the lensing issue in the Planck data that I'm going to explain in a second. So this first one is the plot related to the power suppression, where now we see here in green and red the results for the bouncing cosmologies, and we see that it's in a better agreement with the data compared to lambda CDM. And then this one here is the one related to the dipolar anomaly. And these are the results for the bounce, where we see that for low L, we have this non-zero value of the estimator A1. This one is the one related to the odd parity preference. And here we have the green and red representing the bouncing results, which then get closer to the observational result. And the blue dotted line is the expected lambda CDM1, which represents the parity neutrality. So it alleviates the three anomalies altogether. So just by doing that, it's already a very interesting model. And some other benefit they find is that you are in agreement with the AL parameter in the Planck data. So this AL parameter, it was a consistency check that was introduced in the Planck analysis in such a way that when you do a best fit, you should recover that this parameter is 1. And then what happens when you assume lambda CDM is that this parameter is around 2 sigma, I guess, from 1. While the result for the bounces, they approach, they get closer to the 1 value that is expected. So it's a very interesting scenario from the phenomenological point of view, because it alleviates these issues on very large scales, all of them just with one single scenario. And on the other hand, it's also theoretically motivated, for instance, in the case of loop quantum cosmology. So we thought it was very interesting to check whether you could really find an imprint from these scenarios in the CMB data. And our hope was to find something at the bispectrum level because of the presence of such large non-Gaussianities. So in principle, it was expected that the bispectrum would be in agreement with the data because these non-Gaussianities are only present on very large scales. And then it's expected that cosmic variance will always overcome the signal. But we decided to check it more carefully. So just to recall, here we have the temperature anisotropies decomposed in terms of the spherical harmonics with the coefficients ALM. And then if we get the 3-point correlation function of these coefficients, we'll get the bispectrum. And this quantity here is the one that we actually measure, which is the reduced CMB bispectrum. And here is just a Gaunt factor that is related to these Wigner symbols here in such a way that you assure the triangle is formed in the sky. And then this is the quantity that we want to compute theoretically and then compare to the data. So this bispectrum is given by this expression here, where you can compute it from the primordial bispectrum that you have, so the one that I showed previously, which has this exponential decay. And this T here is the transfer function, and the JL is the oscillating spherical Bessel function. And here we have the X variable just to integrate and assure the triangle configuration. And here we have the modes K1, K2, and K3. So this is a fast oscillating function, this one as well. Here we have an exponential decay and some other powers in the K1, K2, and K3. So this integral becomes a mess, and even numerically it's a bit challenging to perform this integration. So the way out that we found was to consider so first we write this bispectrum in such a way that it's separable. So we define the XL, ZL functions where we do the integrations in K and in X separately. And then what one gets is that you have this function XL of X that will peak when the argument of the transfer function is the same as the spherical Bessel function that you have here. So when the X is equal to the T0 minus T decoupling. And this form here of the transfer function, it's mainly valid on large scales in principle. It's an approximation. It's not a full numerical transfer function. So we started with this one to have an idea about the signal to noise ratio. And this is valid mainly in the Sachs-Wolf plateau, which is the region that we are interested in. And then we get this peak of this integrand when these arguments are the same. And it will also depend on the multiple that you have. So for multiples like 10 and 15, it will have this broader peak, while in L, 95 and 100, you have something that is a bit more narrow. And then we regulate this accordingly in order to perform this integration and neglect the parts that are outside the main contribution. And then by doing that, we compute numerically the reduced bispectrum for this scenario. And this is the result for loop quantum cosmology. And for the other scenarios, the plots are all very much similar. So here we have the bispectrum as a function of the product of the multiples, L1 and L2 and L3. And here the blue dots represent the numerical results that we have. And in black, we have a fit that was obtained by means of this product, which is surprising because we were expecting something in terms of the sum of the multiples, but the fit is better in terms of the product. And here we have the same result, just showing in 3D in order to show the multiple dependence. So here we plot L1 and here L2 equal to L3. And here we have the result for the bispectrum, where the gray plane corresponds to this fit here. And finally, here we have the bispectrum, which is still the reduced bispectrum. So the capital B here is just because it's a different paper, so we used a different notation, but it's the same quantity as this one. And this is in order to show the shape of this bispectrum, where we see that it peaks in a region that is similar to the local bispectrum, but it decays much faster than the local one. So what we see in these plots is that indeed the bispectrum decays exponentially, as was expected in the literature. But nevertheless, we see that on very large scales, the peak is the behavior goes, like the bispectrum goes up very quickly. And then our hope was that we could maybe detect this bispectrum in these very low scales. So in order to do that, we have to compare these results with cosmic variance, and we also compared it to the local bispectrum in order to see how larger it is on large scales. So here we computed the variance of the bispectrum, and then we relate this to the variance of the reduced bispectrum, which depends on this factor here, which is related to the Gaunt factor that we had previously. And then this will be cosmic variance. So we compute cosmic variance for each of these multiples, and we see that indeed cosmic variance is always larger than the signal in principle. So the signal here is the one in blue, and in gray we have cosmic variance. And for comparison, we plot the local bispectrum with an FNL of 5, which is the one that is constrained by the Planck data nowadays. So we see that the signal is indeed always larger than the local bispectrum on these scales. But cosmic variance still overcomes everything in principle. But if you pay attention to the very large scale, so very low L, you see that if you fit these points, at some point here, the signal overcomes cosmic variance. So this is the region that you can use in order to find imprints in the data. And this is only possible because when you compute the signal-to-noise ratio, we are computing the cumulative signal-to-noise. So here we have this expression where our signal is the bispectrum. At this point here, our noise is just cosmic variance. And then we sum over all the possible multiples from 2 up to some maximum multiple. And because you do it over and over again, what we see is that you keep summing this signal where it slightly overcomes cosmic variance for very low L. And then what happens is that you keep summing it many times. And then in the end, you get a signal-to-noise ratio that is considered high. So for instance, for the loop quantum cosmology case, we get a signal-to-noise ratio larger than 25. And this is already enough in order to be detected in the Planck data. And this is also similar to all the other bounce scenarios considered. All of them are above, all of the signal-to-noise ratios are above 10, which is then considered enough in order to perform a detection. And then at this point, we were wondering first whether people have looked into this kind of bispectrum shape already, because let's say that this bouncing bispectrum has a significant overlap with the local bispectrum. Then it means that the Planck collaboration has already done the analysis for the local bispectrum, and we could straightforward say that this bispectrum shape was not detected in the data. But this is not the case. So this bispectrum shape is very specific to this scenario. It decays much quicker than the usual bispectrum shapes that are known in the literature, like the local, the orthogonal, the collateral. So we performed the inner product between each of these bispectrum, so the bounce and the local, the bounce and orthogonal, and so on. And what we find is that the inner product is always very low, which means that the shapes are very different, and we cannot use the existent constraints in order to say that the bounce bispectrum was constrained or ruled out. So we had to do the analysis for these kind of bispectrum shape from the beginning. So the first thing we had to do was to go back a few steps, because if you remember, we used an approximation to the transfer function, which is in principle valid in the Sachs-Wolf plateau. But because now we are interested in comparing this with the actual Planck data, we have to be more careful and take into account the full numerical transfer function, not only the Sachs-Wolf contribution. So we obtained the full transfer functions by using a Boltzmann code. You could use class or CAM. Here we have the plots from class. And what we see is that, for instance, for L2, we have a discrepancy between the class transfer function and the analytical transfer function that we used before. And for L15, the agreement is a bit better, but there is still some difference. And if we remember that the signal to noise has the main contribution from the very low L part, it's important to take into account this difference here for such low values of L. But what we find in the end is that regardless of this change in the transfer function, you will still get a signal to noise ratio that is large enough in order to be detected in the Planck data. So here we have the new results with the full numerical transfer function, which are the dark blue dots. Then we have this light blue line, which represents the fit that we had in the previous computation with the approximated transfer function, and in yellow, the local bispectrum. And here we see that this light blue line, it overestimates the bispectrum for such very, very large scale, so for very low L, which is the most important region for the signal to noise. But nevertheless, this result here still leads to a signal to noise ratio that is large enough in order to be detected in the data. So here we have the comparison in 3D, just to show the comparison with the local shape, where here we just chose all the values of FNL the same. So that's why now the local bispectrum looks much larger than before. So this one is not with FNL5. And we see that the shape is more or less similar, but because it decays much quicker, you cannot compare this, for instance, with the local bispectrum and the constraints that we already have for the local bispectrum. So now we used this full numerical result in order to analyze the values of FNL that will be allowed by the data. So we do that by defining this estimator, which is formed by this inner product between the theoretical bispectrum and the observational one, and then normalized by the inner product between the theoretical with itself. So this inner product is defined in this way, where here we'll have the noise, and this includes the instrumental noise, and here you have the reduced bispectrum A and B, which could be the theoretical or observational. And in this analysis, we also used the binned analysis, which is okay as long as this bispectrum, the signal here is smooth, which is actually the case also for the bouncing scenario. And then we also compute here the correlation coefficients by using here the Fisher matrix, where we have the Fij defined as this product of the Bi and Bj, so bispectrum I and bispectrum J. And then we get this table here that will show the correlation between different shapes and the bouncing shapes. So here we see that the inner product with the local shape is small, the same for equilateral, the same for orthogonal. It's more, it has a larger value for the orthogonal case, but nevertheless, it's still a small value in such a way that you cannot just get the constraints from one of these shapes and put it on the bouncing bispectrum shape. And we also see here the correlation between the point sources, cosmic infrared background, and lensing, which are possible noise sources in this case, but they are also small. And here we have the correlation between the bouncing bispectrum with loop quantum cosmology, which is this one with Q minus 0.7, and this one here is the phenomenological bounce with Q minus 1.24. And then we have this correlation here of 0.91, which is expected. And then finally, what we get for the FNL here from this estimator is that for the loop quantum cosmology case, which is this one here, you have an FNL constrained to 160 plus or minus 260. And then for the phenomenological case, we have 19 plus minus 34. And if you remember the table that I've shown previously, in order to have a p-value of 20% for the power anomaly, the power suppression anomaly, the FNLs that are required are much, much higher than that. So of order 8,900, so much larger than these values shown here. And this leads to an exclusion of these scenarios by 6.4 sigma and 14 sigma respectively. So here I would like to stress that it doesn't mean that, for instance, all these bouncing scenarios are excluded. It just means that if they have enough non-Gaussianity in order to alleviate the CMB anomalies, then they are excluded. So this is the result that we got from this project. In case you're not interested in alleviating the CMB anomalies, you can still have loop quantum cosmology and all the other possible bouncing scenarios, and they are not excluded by the data by no means. So finally, I would like to talk a little bit about the implication for loop quantum cosmology and some recent updates in the literature. Because I think it's a very interesting result that was obtained by Roshna, K, and Srinath. And here we have this publication in this preprint where they developed these results. And the main point, the main difference with respect to what we've done is that previously in the literature, we have the power spectrum that is represented by this figure here. And previously in the literature, what people have been doing is to consider this approximation here in this oscillating part. So instead of considering all the oscillations here in the power spectrum, we consider just the scale dependence here, and then move on to the usual scale invariant part. And then what they found was to indeed take
we have 5 minutes left.
Okay, thank you. And here we have these oscillations in the power spectrum that were then taken into account by Roshna and Srinath. And then what they find is that the FNL, because it has this dependence on the power spectrum, it will also oscillate. So it has the exponential suppression that we have taken into account, and that was already taken into account in the literature, but this factor here was taken into account for the first time. And it takes into account these oscillations here, and it goes as 1 over the scale of inflation. And this scale here is of order 10 to minus 6, so this becomes a very highly oscillating function. And once you do that and you perform the integrations, these oscillations wash out in such a way that you would suppress this bispectrum altogether. So then this is the result that they find in their paper, which is a bispectrum that is extremely low, even though it has some significant value of FNL. So this has some differences with respect to what we have done. So the first thing is that the scale of the bounce is different. And this is important because if you consider a bouncing scale that is lower, you need to require a higher FNL in order to achieve the same p-value for the anomalies. So it becomes a bit harder to solve the anomalies if this scale is smaller. But then in principle, because this power spectrum is suppressed with the oscillations, in principle, you could still have a very large value of FNL, and then the oscillations would wash out and you would not see the reduced bispectrum in the data. But another point is that these oscillations, they also have an impact on the non-Gaussian modulation that I've shown earlier. So we had this modulation in the power spectrum that was introduced by this FNL, and because it has this oscillating feature here, it also decreases the modulation that you can perform. So if you take into account the oscillations, it's very difficult that this scenario will be able to alleviate the anomalies. So this is, I think this result shows once again that loop quantum cosmology and other bouncing cosmologies are not excluded by no means. but it's hard to solve the anomalies with them, because even in this case, the modulation, the non-Gaussian modulation will be much less efficient than the one that you get when you only consider the scale dependence here, but not the oscillations. So to conclude, I would like to point out the main findings of our work. So the first thing that we found is that these scenarios that are able to mitigate the anomalies, they are excluded by the Planck data. You can still have these bouncing scenarios followed by inflation with some different value of FNL, and then this is by no means in contradiction with the bispectrum data in the Planck collaboration. But you cannot alleviate the anomalies. And even if you consider the oscillations, because you suppress the modulation that you have in the power spectrum, I wouldn't expect you want to be able to solve the anomaly in this case. And the results are similar if we are a bit more flexible, and instead of considering a 20% p-value, we consider something lower. So for instance, let's say 10% p-value. This still leads to a very significant exclusion of these scenarios. And then for the p-value of 5%, the exclusion is lower, but then like how much do you gain from 1% for lambda CDM and 5% in these scenarios? So it's then not that much appealing anymore. And this shows the sensitivity of the Planck data to scales that go beyond the pivot scale. So usually we think that we can introduce new physics on such large scales because we will not be able to see them in the data. And I think this result shows that we have to be a bit more careful in order to do that. Because especially if you have non-Gaussianities, we see the transfer functions and we see that they are not delta Dirac functions. So for one single multiple, you have a dependence on many values of k. And then this leads to effects that are in principle outside the horizon to have impact on physics that are on large scales. And especially in this case where you have a very large non-Gaussianities, you might be able to see them in the data. And this is valid not only to this bouncing scenario case, but also to any other proposal that used skewed statistics and non-Gaussianity in order to alleviate the anomalies. And finally, we have these very interesting results regarding the oscillations in the primordial bispectrum that are taken into account, which then average out in the reduced bispectrum. And from my perspective, this is very interesting because in principle, you could have an arbitrarily large FNL, so a huge amount of non-Gaussianity, and still not see it in the data. So from my point of view, it would be interesting to see whether one could find some other way to probe the presence of such bispectrum in another way that it's not the reduced bispectrum. And then this is expected to reduce the effects of the non-Gaussian modulation. So even if you take the oscillations into account, when you try to modulate the power spectrum in such a way to alleviate the anomalies, the oscillations will work against the modulation. So it's still very hard to solve the anomalies in this context. And finally, I think the main message is that exploring quantum cosmology through data that we already have isn't hopeless. So even though we have modifications on very high energy scales, it might still be possible to find interesting prints and constrain some classes of scenarios. Thank you for your attention.